All right, so today we're going to talk about time-dependent voltage sources in preparation for time-dependent circuits. So far we've dealt with DC sources, batteries, voltages that are constant in time and have always been on. Now we're going to start moving to AC or sinusoidal voltage sources. In fact, in general, we're going to talk about signals that vary arbitrarily in time, but to do so, we're effectively just going to concentrate on sine waves. So here's a sine wave here. Now it's curious that we can actually concentrate on sine waves and get everything we need to know. And there's a few reasons for that. So why sine waves? Well, first of all, sine waves are relatively easy to produce. For example, if we have a magnet inside a coil and we're spinning that magnet with uniform circular motion, the voltage that's produced will be a sinusoidal voltage, or actually a sinusoidal current, which can correspond to a sinusoidal voltage when drawn across a load. So that is one reason that we use sine waves. They're easy to produce. Another one is that they're mathematically very nice. Now, one reason is that they are very smooth. Not only the function itself is smooth, but its derivative is smooth, and the derivative of the derivative, and its eighth derivative. The derivative of a sine is a cosine. The derivative of a sine is a sine again, and it goes sine, cosine, continuously. So not only the rate of change is smooth, the rate of change of the rate of change is smooth, the rate of change of the rate of change is smooth, all the way up. So they're very nice to work with mathematically because of that smooth property. But there's a more deep connection between why sines are interesting and useful, and that is that they form the fundamental building blocks of all time varying signals. As long as the functions themselves aren't cooked up in some evil mathematician's notebook, we can represent any function as a sum or distribution of sine and cosine waves. So that is known as Fourier analysis, and we're actually going to talk about it a bit later in the course. But for now, let's zero in on sine waves now that we're motivated to learn everything there is to know about them. And we're going to break it up into two parts. We're going to look at the vertical axis and the horizontal axis, or the time axis. So let's start with that x-axis, or the time axis in this case, and the relevant quantities. Well, the first thing we know, or notice rather, about a sine wave, or a sinusoidal wave, is that it's periodic. It repeats itself after some time. And the time that it takes to repeat itself, well, that's just called the period. The time that it takes a periodic function to repeat itself is the period. In this case, in this example here, it happens to be 0.5 seconds, 500 milliseconds. So the period of this function here is half a second. Now, that tells us how many seconds it takes to complete one cycle. There's a closely related quantity, how many cycles do we get per second, and that is known as the frequency, f. The frequency is measured in hertz, and it is just 1 over the period, right? 1 over the seconds per cycle is cycles per second, and that's the definition of frequency. The units of it are hertz, as we said, and in this case, we have a 2 hertz sine wave. Now, there's a closely related frequency to the frequency, which is called the angular frequency. And effectively, if we recall our analogy with, or our example rather, of spinning a magnet in a coil to generate a voltage, now if we look at the projection of that, the way that field is pointing, and how it evolves in time, that's going to give a sine or a cosine, depending on where it starts. And therefore, after the magnet, or whatever system we're looking at that's uniformly rotating, has gone 360 degrees, or 2 pi radians, we've gone 1 full cycle. So the angular frequency, which we call omega, is the radians per second. So omega equals 2 pi times the frequency, right? So if we go around once per second, we've gone 2 pi radians per second. And it yields a very convenient way of representing the sine wave, because if we recall the sine wave, if we just look at sine x, that has a period of 2 pi. Sine of 0 is 0, and it goes to 0 at pi and starts again at 2 pi, and then it repeats itself again at 4 pi. In fact, if I just take any part of that sine wave, x, sine of x, that's going to be the exact same as if I took sine of x plus 2 pi, 4 pi, 10 pi, or 2020 pi. So this allows us to write just sine omega t for a sine wave. And it turns out that I'd say it's at least as useful as the normal frequency f. Now, one important point is that the units of frequency, the units of angular frequency rather, is not hertz. When you say hertz, you mean f. The units of omega is radians per second. Okay, so typical values for electronics start around 10 hertz. The voltage coming out of your wall is 60 hertz, at least in North America. It'll be 50 in other places. And the electronics we deal with will be kilohertz, megahertz, maybe even up to gigahertz. After that, it gets pretty tough to talk about microwave frequencies, which are at terahertz. And it's almost impossible to make circuits work at tens of terahertz. If you go to hundreds of terahertz, well, that's called electromagnetic radiation or light. So I have a laser pointer here. So there's about I don't know, maybe 700 terahertz or maybe 600 terahertz signal there. So there's another important quantity in the time axis, and that's phase. So in our analogy, again, we had our spinning magnet, and at time equals 0, it might have been perfectly aligned so that the voltage at that point happened to be 0. But that would be kind of a lucky random starting point. What if I started somewhere else at time equals 0? Well, I'd still have the same overall pattern, but it would be shifted left or right in time. And I can represent a shift in a function. If I have f of t, I can represent the shift in that function as f of t plus delta t, whatever that shift is. And that leads to what is known as the phase. So here's the phase of my signal here. I have my phase equals 0 dotted sine wave here. And I actually have I think about a 60-degree phase shift, or whatever I put in there, for the orange one. Now remember, if you have f of t and you go f of t minus 2 seconds, it'll be shifted to the right by 2 seconds, right? If I go f of t plus 2 seconds, it'll be shifted to the left. So if I have a positive phase shift, it actually gets shifted to the left. And psychologically, sometimes it looks like it's got left behind, but it's actually faster. It already crosses 0, like negative half a second. It's ahead of where it would have been for a 0 phase. So a positive phase means a shift to the left, but that's actually an advance in time, and we call that a phase lead. A negative phase shift is called a phase lag, corresponding to a shift to the right. So that's the phase shift here. But again, a phase shift is just a shift in time, and we can actually explicitly write that out. So let's factor out the omega here, and we see we have omega times t plus phi over omega, or phi over 2 pi f. Okay? When we get that, we actually have t plus some other thing, and that's just units of time. That's a time shift. So our time shift is actually just phi over 2 pi times f. We can rearrange that and write it explicitly as a linear relation. So the phase shift is just omega times t. Rather, 2 pi times f times my shift in time is the resultant phase. Another way I'd like to write this sometimes is that phi over 2 pi is the same as t over the period. So what fraction of 2 pi I have is what fraction of a period I've gone through. Okay, so there's one more thing I want to say about phase shifts. Now, if you remember way back when you're doing trig identities, there's this identity sine of a plus b is equal to sine of a cos of b plus sine of b cos of a. And we can apply that plugging in a and b, for a and b, omega t and phi respectively. So if I plug in that formula, that addition formula for sine omega t plus phi, what I find is that I get sine of omega t times some number, cos of phi, plus cos of omega t times some number, sine of phi. So I can represent a phase-shifted sine wave as just some combination of sine and cosines, of pure sines and cosines. And if my phase happens to be 0, if phi happens to be 0, then I get a pure sine wave. If it happens to be 90 degrees, I get a pure cosine wave. But in general, I'm going to have some random phase shift, and that means I'm just going to have some combination of sine and cosine. A phase-shifted sine wave is just some combination of sine and cos. Now, how this is written sometimes is I and Q, quadratures as they're called. Where this comes from is that if I have a sine wave, I can talk about things that are in phase with it, or the I, that's the sine part, or in quadrature, which is the $10 word for 90 degrees out of phase, with my original sine wave here. That's the I and Q quadratures. And any phase-shifted sine wave can be broken down into its constituent quadratures. So that's an important piece of nomenclature that you'll sometimes hear. Okay, that's it for the time axis. Let's talk about the voltage axis, the vertical axis, and some of the related quantities. The first one, perhaps the easiest one, is the amplitude. That's just the number that we're multiplying sine by, and it tells us the maximum value that the sine function is going to reach. The maximum value is when sine is equal to 1, in which case my voltage is, at that particular time is equal to V naught. That's what we call the amplitude. Easy enough. There's a related quantity which tells us the range of values that we can get. It's the maximum minus the minimum, and it's called the peak to peak. So the peak to peak tells you the range of possible values. For a sine wave, it's kind of redundant if you already have the amplitude. It's just twice the amplitude. But it's very useful for signals that are a bunch of sine waves or noise, just random noise. We want to know how much the maximum deviation from zero we're going to get is. And that's when we use the peak to peak a lot. All right, there's one more seemingly obscure quantity that's actually used all the time, and that's the RMS. And that is the amplitude divided by the square root of 2. Seems suitably arbitrary, but why is that root 2 there? Well, what the RMS is actually hidden in the name. RMS stands for root mean square. So the square, that's easy enough. We take the voltage and we square it. The mean means the average of the function over its interval. So how do we calculate that? We take the integral of the function over the full period, divided by that period, and that is the mean. So if I do that, the mean of the square, I have the mean square. And the root mean square is I just take the square root of the whole thing. So that's the RMS voltage. But again, why is it root 2? Well, to see that's root 2, we just have to do a bit of math. So let's just plug it into our formula that is hidden in the name of the thing that we're trying to calculate, the RMS. Let's actually just calculate the mean square to start with. So here's the square, v squared sine squared omega t, and we'll take the mean of that. We'll integrate it over t. To make math easier, let's just do a change of variables. We'll call tau 2 pi times t over the period, and that simplifies the integral a tiny bit. It gets rid of the period, and it makes our bounds of integration just between 0 and 2 pi. Now to integrate sine squared, there's a number of ways to do it. I think the one that I always remember is there's a trig identity. Sine squared of x is like a half minus a half times cosine of 2x. And then that's an easier thing to integrate. We do that here, and we just get tau over 2 minus a quarter of sine 2 tau. And we've factored out an extra factor of 2 here. In fact, that sign there, it does nothing. It does nothing. It's because it's the same value at both ends of the integral. So the tau is the only thing that matters here, and that gives us a factor of 2 pi. And when we do that, we get that the RMS squared is equal to V naught squared over 2. So the RMS, we just take the square root, and we get our V naught over 2. And that is where we got this number from. Okay, so those are the vertical axis things we wanted to talk about. Now there's another concept here, namely that there's a lot of redundancy. Let's go back and look at we have it here, our sine wave here. We have a 3 volt sine wave, it looks like, at 2 hertz with some phase shift on it, maybe 0 phase shift now. But anyway, imagine if I had to store this on a computer. So I could write down the value of the function at time equals -1 millisecond, at negative 0.999 milliseconds, 0.-9998 or 998 milliseconds, so on and so forth. I could specify as many values as I want. There's really no point. So first of all, there's certainly no point storing more than 1 period's worth of information because it's periodic. It just does the same thing after that. But it's even more redundant if we know ahead of time that it's a sine. All I need to know is 3 numbers, basically. I need to know the amplitude, the phase, and the frequency. And then I don't need to write down, I know what the value is. I can calculate it at all times. So thinking about sine waves in terms of just their frequencies and phases leads to the concept of the frequency domain or frequency space. And we talk about that a lot. rather than the value of the voltage at all times, we just look at a given time, what are all the frequencies that voltage is made out of? So in frequency space, we're just going to plot the amplitude at the given frequency. So here I have a sine wave, and it has all these redundancies. It's a 3 volt, 2 hertz sine wave with a negative 60-degree phase on it, apparently. And I can just represent that as a single point in frequency space. A single point in frequency space. By the way, I'm pointing at a green screen here, so your guess is as good as mine. Actually, your guess is better than mine as to whether or not I'm pointing at the right thing, just for your information. So in this case, we're only plotting the amplitude at that frequency. We might also want to know the phase. Not always. Sometimes we just want to know what the kind of the RMS of that signal is. But then we can just write either a three-dimensional plot with time down or frequency down one axis, magnitude and phase. That looks very fancy, but it's often more useful just to write it as two-dimensional plots where we're looking at the phase versus frequency and the amplitude versus frequency. And that's what we've done here. So this whole thing is represented by these two numbers at those frequencies. This should be ringing a bell if you're fresh out of math class. We need to store a magnitude and a phase somehow. And there's a mathematical tool that makes that very useful to store magnitudes and phase. It's called complex numbers. A complex number has a magnitude and a phase. So we're going to represent our voltages and our currents and our resistances, or impedances as they will be called, by complex numbers. And what's great about this is these complex numbers already have built into the magnitudes and phases. But it gets even better, because there's a beautiful theorem in complex analysis, Euler's theorem, that tells us that a complex exponential automatically relates trigonometric functions to complex numbers. Not only that, any complex number can be written as a magnitude times this complex exponential. So for free, we get sines and cosines while representing magnitudes and phases. It's almost too good to be true. We can represent all signals by these complex exponentials. So a voltage might look like this. Okay, so you might be thinking, yeah, but what does it mean to have a complex voltage? Now, it's often said that, complex voltages are imaginary, there's no such thing, and I cannot agree with this. I think they are. I think complex voltages is just a succinct way of writing the magnitude and the phase. Sine waves aren't really real in some sense. They're a mathematical function as well. And complex numbers are just another way of looking at quantities that have a magnitude and a phase that vary in a certain way over time. And I think there's nothing imaginary about it. We just need to know how to extract the information. The common trick is to represent your voltage as a complex exponential, as we've done here, and then in the end, take the real or the imaginary part. If you want to take the real part, because that sounds more reasonable, that's fine. We just, as a result, get the cosine quadrature. So we're looking at the cosine quadrature of the component by taking the real part. The imaginary part, that gives us the sine quadrature. In fact, we can take any projection of this voltage that's varying with time, and we're going to get a realistic quantity from it. But to be honest, in this course at least, we often don't even bother taking the real part. We just have our complex voltage, and we divide it by our complex resistance, and we get the complex current. And we leave it complex. We just say, okay, here's the amplitude of that complex number. That's how many milliamps I have. And here's the phase. That's how delayed it is to the left or to the right. So from now on in the course, we're going to be writing the voltages and the currents in two ways. We're going to either write sinusoidal functions when it's convenient, or equivalently, we're going to write them as complex exponentials. 6 in one, half a dozen in the other, really. Often the complex exponentials are going to be much simpler to use in our math, but sometimes we'll just go with the sinusoidal representation. So that's basically all I wanted to say about this brief speed run through sinusoidal signals in electronics. We'll start using them in the next video when we talk about complex impedance and frequency response of filters. But the takeaways, I guess, for this are: one, don't be scared. We're going to use complex numbers for voltages, but it's just a way of keeping track of the magnitude and the phase. We'll see how easy it is when we start working with examples, and it's going to save us a lot of trouble. The next important thing, I think, is that there's a magnitude and a phase associated with sine waves, and we can either think about them as things that happen in time, or frequencies which are happening at a given time. All right, so we can talk about time domain description of a voltage going up and down like this, or a frequency domain description which represents what happens to all the sines and cosine waves. Finally, just a reminder what a phase is, we're going to come across it a lot. It's merely a shift forwards or backwards in time. And keep that in mind when we're talking about the phase shift, the lead or the lag of high pass and low pass filters. All right, so thanks for bearing with me, and I'll see you next time.